Hello. So today we're going to prove an exercise related to the order measures, and it is I think exercise 1.18 on Folland. Let me just find the problem and then copy down on my iPad. Oops. Okay, so let's read the problem together. So we have A that is in the power set, and let A be an algebra, and let this be a collection of countable unions of sets in A, in the algebra, and let this be the collection of countable intersection of set in A sigma. So sigma will always denoted intersection, countable intersection, and delta always used for intersection. So sorry, did I say? So sigma is for union and delta is for intersection. Okay, and we also have let mu naught be a premeasure on A. So let mu naught be a premeasure on A. And mu star be the induced outer measure. So if you remember the definition for mu star, right? Okay, mu star of A is equal to infimum summation 1 to infinity and mu EJ mu naught EJ, where EJ is a subset of X, and in particular it is in A, and A is a subset of union of EJ. Okay. Okay, so that is the definition, right? And let this be the premeasure on A, and this is in so specifically is outer measure induced by the premeasure. Okay, let's prove A. So for any A in X and epsilon larger than 0, there exists A in the collection of countable unions of sets in algebra with E in A and mu star of E smaller or equal than mu star of E. Mu star of A smaller or equal than mu star of E plus epsilon. This is purely the definition for outer measure. So let me change the definition here. So I use E to denote this, and I use AJ to denote this. So AJ and AJ. Okay. So we have by the definition of infimum for all epsilon larger than 0, there exists sequence of AJ in A with AJ with A the subset of union of AJ, and summation mu naught of AJ is smaller or equal than mu star of E plus epsilon. But we also know that by the countable additivity we have this is larger or equal than mu naught of union of AJ, right? And then also because AJs are the sets on the algebra, right? And we know that the outer measure is an extension of the premeasure on the algebra. So what I'm saying, this is equal to mu star of union of AJ. And notice that the union of AJ belongs to a sigma, and therefore we're done with this problem. And for B, it is a little bit more complicated. So suppose, so before that, I want to give an intuition idea. So for example, if you have your universal set X, it's to be have infinite measure. And if you have E, and let me see if I am sharing screen. Yes, I am sharing screen. Okay, so we have this, right? And then it is saying that for every epsilon, I can find a set A that is not too big, is not too much bigger than E. How much bigger with measure epsilon, within epsilon. And the next, let's read the problem B. So it's more complicated, it involves more concept. Okay, so we have mu star of E is finite, and here mu is mu star measurable if and only if, so you read it this way, there exists B from this collection where E is a subset of B and mu star of B star minus E is equal to 0. So the first time I was reading this problem, I have no idea what I should do. So don't worry if you don't have any like intuition when you first saw this problem. We're gonna work it together. So let's work on the forward direction. So suppose mu naught of E is finite and E is mu star measurable. So E is mu star measurable. What does that mean? That means that equality, right? Mu star of E is for every f subset of x, mu star f is equal to mu star f intercept E plus mu star f plus mu star f intercept EC. Okay, so we have so say we have this, and we want to show, right? There exists B in a sigma data with E the subset of B and mu star of B set minus E is equal to 0. So the idea of proving the existence of something is always my like the weaker weaker side. So here the strategy is like, or the procedure is you propose something, right? Before you propose, you write something or draft, or you thought about it, what could work, and then you prove with the thing you propose it satisfies the required property. So here, our intuition. So again, this graph X, and here is E. Here is E. And it is saying that there exists B in this specific collection such that E is still a subset of B. So here I'm going to write this. And instead of, so here, right, instead of having measure that is less than epsilon, what I'm having right now here, it is saying that mu star of E, mu star of B side minus E is equal to 0. This should be mu star of A side minus E is less than epsilon. Okay, so that's the difference. And then, well, the first graph and the second graph are very similar, and they haven't given us an intuition how to define our B. And also from the hint, right? B is in this set, so it should be intersection. It should be intersection of the union of something. Okay, so by A, for every K in N, there exists, let's call it EK. there exists bk in a sigma with E is in bk and mu star of E is smaller or equal than I'm sorry, mu star of bk is smaller or equal than mu star of E plus 1 over k. And now you take B to be the intersection of bk. So of course this is in mu sigma delta. And what E is a subset of B. So the only thing you need to show for the remaining part is so it's to show this. How do we show this? Okay, observe that since B is the intersection of this amontosity, right? We have mu star of B is smaller or equal than mu star of BK, and which is smaller or equal than this for all k in N. And that implies mu star of B smaller or equal than mu star of B smaller or equal than mu star of E. But E is a subset of B, so mu star of E is smaller or equal than mu star of B. Therefore, we have mu star of B is equal to mu star of E. And since think about this. Okay, since we assume that E is mu star measurable, B is in A sigma delta, which is a collection of sets in mu sigma, right? And mu sigma is union of sets in A. So my point is B is mu star measurable because because mu star measurable is a sigma field, is a sigma algebra. So the infinite union is also in that sigma algebra. Okay, so we have E, so we have E union B side minus E, right? We have those two is equal to E, and then they are disjoint, so they're disjoint union. So mu of E is equal to mu of E plus mu of B side minus E is equal to mu of B and mu star. And mu star B side minus E is equal to mu star B minus, okay. which is equal to 0. So therefore we're done with one direction. So conversely, right? So suppose let me copy the suppose there exists a B in a sigma delta with E the subset of E and mu star E sine minus E is equal to 0. We want to show that E is mu star measurable. Okay, how do we do that? There are some ways, like when you first think about the proof of mu star measurable, you might want to use the definitions, but here actually you don't need to. Here is actually you can try to find that the set E can be written as union of two mu star measurable sets, and therefore because the sets are because the mu star measurable collections in algebra, then any union is going to be also in mu star measurable. So that is the key observation for this problem. Okay, so the observation is B sine minus E is a subset of X. And mu star B sine minus E is equal to infimum again. So for all epsilon, there exists a k in A such that B sine minus E is subset of union of AJ, sorry, AK, and mu star B minus mu star union of AJ smaller equal than mu star B sine minus E plus epsilon. And if we name this as A, so we have mu star of A smaller equal than this. I mean, we're given this is equal to 0. Right. So epsilon goes to 0, mu star of A is equal to 0. Why do I want to know that? Well, that means A is a null set of mu star. So mu star null set. And then what does that imply? A is a null set of A, new set with respect to mu star. Okay, what's the relationship between, right, so notice that B set minus E is inside of A. That implies B set minus of E is also a null set of mu star, and by the completeness of mu star, we know B set minus A is mu star measurable. Is mu star, because even though we're given mu star of B set minus E is equal to 0, that doesn't necessarily mean that mu star B is mu star measurable. B minus E is mu star measurable. Okay. I think we're almost done. So E is equal to B sine minus E. I want to express B in terms of the things that I know, and then they are mu star measurable. Since I have E and I have B, well, I know B sine minus E, which is this, is mu star measurable. And because B is from A sigma delta, I know this is also, I know this is also mu star measurable. So it doesn't matter how to express B in terms of this. If you recall, so B side minus E, C intersect B side minus E complement intersect E. No, that doesn't make sense. So there's a very important observation. It's actually given. So E is a subset of B. I think it's given, right? We didn't use this. So because E is subset of E, let's see, this is B, this is E, and we want to express E in terms of beta minus E, right? So what does that mean? So E is equal to B set minus E, which is this region, right? B set minus E complement, complement, and that means I am looking at here, I'm looking at here as well as here, right? But here, I don't need the outside part. I don't need the outside part. So therefore, I just need to intersect with B, right? Okay. So notice that this is mu star measurable. Therefore, the complement is mu star measurable, and this is mu star measurable, and hence E is mu star measurable, and then we're done. So there are a couple things that needed to be careful when you're doing. I think there is also part 3. Let me copy the problem down here. So if mu star is sigma finite, what does it mean by sigma finite? Right, that means X, right, there exists AJ from 1 to infinity, and X is equal to union of AJ. X X is equal to the union of AJ, and where the measure mu naught of AJ is finite. That means mu naught is sigma finite. Okay, the restriction mu star E is finite in E is superfluous. What does it mean by superfluous? I think it means redundant. Let me double check. Yes, I was right. So, so when we look at part B, so basically we need to prove part B again, but without replace this constraint with the constraint that mu naught is sigma finite. Okay. Oh, sorry. Replace this with the constraint that mu naught is sigma finite. So in this case, we assume E is mu star measurable, and we know this is sigma finite, and then we want to prove the existence of such B, okay? So the proof is a little bit complicated, but the basic idea, so here is the basic idea. We have, so before, if you recall A, right, we have the finiteness, or before the original part B problem, it has finiteness assumption on the measure, right, on the mu naught measure of E. And if we have sigma finite, then the most intuitive next step is to split your E into small pieces where each pieces is finite, small disjoint pieces that each pieces is finite. So what we're gonna do is we're going to use sigma finiteness to write, okay, let's just write. Because using sigma finiteness to find the existence of such collection, and we have X is equal to the union of AJ. Okay, and what do we have? What do we have next? Let me think. What do we have next? Is right. So what do we want to do? Is we want to define. Let me write it clearly. So define EJ is equal to E's intersect AJ. So we want to do that. So I call, right, and I call this EJ, okay? And we know that the mu naught of EJ is finite. And then we can apply the results, right? On each EJ. So let's look at the result from B here. No, we cannot use this directly. So what we're gonna do is we're going to, so again, because this is a finite, right? And then by the definition, let me think about this. So we want to use part A. Why do we want to use part A? For each J using A, we can find the CJ in the collection of countable union of sets in algebra such that EJ is in algebra. Okay, so because EJ is a subset of X, and mu star of EJ is equal to what informal of the collection, blah, blah, blah. So that implies there for all epsilon, or for example, fixed K, right? So fixed K for there exists what? There exists Cj in a sigma such that Ej is a subset of Cj and the measure of Ej such that the measure of Cj is smaller or equal than the measure of Ej plus 1 over k, but it has to do with j, so I'm going to write to be 1 over k times 2 to the negative 2j. Okay, so that is by part A, and we're doing this for every j. Okay, and then what is the next step? Or so each of we can do this because each of pieces, so the mu star Ej is finite. That's why we can do this. And then we have mu star Cj smaller equal than or minus mu star of Ej is smaller equal than 1 over k times 2 to the negative j. And because Cj is in sigma algebra and Ej, what are Ej? Ej is equal to the intersection of this. Where E is mu star measurable and Aj is in sigma algebra. So Aj is, like to write like Aj here belongs to sigma algebra. Therefore, those Cj and Ej, they are both sets from sigma algebra, the mu star measurable set. Therefore, you can write mu star of Cj set minus Ej is smaller or equal than 1 over k times 2 to the power of negative j. Okay, and what else? I'm curious, what did I do before? So for A, so for part B, right? I have this. Oh, and I here we cannot just directly do mu star Cj minus Ej is equal to mu star Cj minus is equal to 0 because it is on different each pieces. So what we cannot do if you follow A and want to keep writing mu star of Cj set minus Ej is equal to 0 is and finish the argument. It is incorrect since our goal is to find B. But here you're doing the little pieces, like the claim is true on each little pieces, but you need to show the claim is true on the whole set. So more holistic view of this problem. Okay, so we need to keep doing. So we already have this. And we need to find the set B, right? What could the set be? So notice that the most intuitive idea for set B is because each CJ is what? It's CJ set contains EJ, right? And then they are carefully selected such that inequality holds. We can let let's see, BK is more important than intersection. Let intersection A and B. Okay, so let BK equal to the union of B equal to the union of CJ. So those are the things we just collected from here. Okay, and we want to show that, and notice, so this is the extra step, mu star of BK set minus E is equal to mu star of union J is equal to 1 to infinity Cj set minus E, which is equal to mu star of union Cj intersect EC, which is equal to mu star union J is equal to 1 to infinity Cj intersect EC. Okay, so we have that. And then what do we have? Okay, so we have this. Okay, so we have this. And then notice that both of them are mu star measurable. So this is mu star measurable. So this is a mu star measurable. And are they, they're not necessarily disjoint, right? So we cannot use we only use less or equal than summation J is equal to 1 to infinity mu star Cj intersect EC. And notice what is this? This is J is equal to 1 to infinity mu star of Cj set minus E, right? And we earlier proved here. So let's just write here smaller equal than J is equal to 1 to infinity 1 over K times 2 to the power of negative J, which is equal to 1 over K. J is equal to 1 to infinity 2 to the power of negative J. And for this, we proved last time in previous video. So this is equal to 1. So it's equal to 1 over K times 1, which is equal to 1 over K. And therefore, we have, like there exists the BK such that this is smaller or equal than this. Let K goes to infinity. What we have is, wait, let me see, because it's also on the left, it also depends on K. BK. No. Let me think. So what we have is So we found the BK such that, okay, so let B equal to intersection of BK. And we want to show that B set, the measure of B set minus E is going to be, right, so the measure E set minus E is equal to intersection K of BK set minus E, which is equal to K BK intersect EC, which is equal to B, which is equal to mu star of intersect K BK intersect EC. C is smaller equal than just one of them, right? Because the background tells me measure. So BK intersect C. Okay, and then this is equal to BK set minus E. And we know this is 1 over K. And now you let K goes to infinity. We have mu star on the left. It does not depend on K. Is equal to 1. Is smaller equal to 1. And therefore, because the measure always non-negative, is equal to 0. And then we're done. Right? And you might wonder, do we need to show the other direction using the hypothesis that mu naught is sigma finite? But notice that when we were proving the other direction in part B, we actually didn't use the hypothesis that the mu naught measure of E is finite. So we're basically done with this proof. We can give a quick summary. So here this problem help us to explore I don't know if we have an E inside of X, then it kind of like help us to explore the set that contains E and how much bigger can it be, and then how much smaller can it be. And if it can go really, really small, then will the measure of the difference between the larger set and the set E be 0 or not? So for part A, we assume that so E is in X and the sigma and then epsilon is larger than 0, and then we're trying to show this, right? The existence of A, and we use the definitions. And then, so A is pretty good to deal with, and then by definitions. So while you were doing A, you should think about the definition for auto measure. It's basically, so you have a measure, you have a set E that is a subset of X, or you can say there is a E in your power set, right? And then you're looking at, in this case, we're talking about the auto measure induced by the algebra, mu naught, the premeasure mu naught. So we're going to look at the set that contains E and the set that are also in algebra. And then we look at all those sets, and then we choose the infimum one, we choose the minimum one in terms of what minimum is the summation of this is minimum. So we're doing each little stuff. I think so. And then we select the minimum one. And then therefore, we have this inequality given epsilon is larger than 0 and the existence of A in A sigma and this inequality. And for part B, it is a little bit complicated and you might don't know what to do when you first solve this problem. So there are two directions. The first direction is, so we always assume that the mu naught of E is less than, is finite. And then the first part is we assume that E is mu star measurable and we try to prove the existence of a specific B such that it is in A sigma delta as well as mu star B set minus E is equal to 0. So we're looking for the specific set given E is mu star measurable and the mu star of E is finite. So what you do is you actually focus on the trick here. So I'm going to highlight the trick. The trick here is you remember in A, you're focusing on E, right? You apply the definition on E and you got this inequality. For B, you apply the definition on B set minus E. And then because B set minus E is a subset of X, so you can totally, it is in the domain of mu star. So therefore you can use the definition for infimum to get this inequality. I'm gonna highlight it here. And then once you get this inequality, notice the difference. And then you define B is equal to the intersection of all of this. And then notice the difference between the relationship between mu star B and mu star BK. The first one is always smaller equal than the second one, and the second one is always smaller equal than mu star E plus 1 over K. And therefore also have the observation that the B and the E, they are, or B and the E complement, they are mu star measurable, and the mu star measurable by proposition 1.11, it is sigma field. So we can actually, and they are disjoint, we can use a countable additivity of sigma algebra or of measure to obtain that this smaller than this minus this is smaller equal than 1 over K, and let K goes to infinity. So we got those two are the same. We got those two are the same. And then once we got those two are the same, notice that what is our original goal is to show that, and then also using the fact that they are belong to mu star measurable collection, which is sigma algebra. So if you can write this, move this to the left, you can get mu star B set minus E. So we obtain that mu star B set minus E is equal to 0, and that finished the first direction in part B. For the second direction, so we're given the existence of such B, and we want to show that E is measurable. And recall that the way to show E is measurable is you can show definitely by definition, using definition. And the second thing you can show is you can write E as a union or intersection in terms of mu star measurable set, and use the fact that mu star measurable collection is a sigma field. So we're going to use the second strategy when proving for this direction. So again, oh, I think I misspoke earlier. For part B, the first direction, we're not applying A on B set minus E. We're applying the definition of A, or we applying the result of A on E, right? On E, this E. And then for the other direction, the trick is that we focus on applying the definition on B set minus E. So there exists a delta such that satisfies this inequality, right? And then we can call the union as A, and then we have this. And because we're given this is equal to 0. So recall our goal in this direction is to show it is measurable. And because this is less than equal epsilon, and then therefore mu star of A is equal to 0. And once mu star of A is equal to 0, and now for every subset of A, it has 0, right? And we prove that for every mu star, for every new set of mu star, it is mu star measurable. Therefore, since V set minus A is a subset of A, because we previously required this, right? The existence of such AK, blah, 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 were chosen based on this criterion, with this criterion. Everything we chose here must satisfy this. Therefore, we show this is mu star measurable. Okay, and because we know this is mu star measurable, and we can express E in terms of B minus E and B, and therefore E is mu star measurable. For part C, it is similar. You just need to be careful because now you have mu naught is sigma finite, while the mu star of E is finite. So remember before you're directly applying you're directly applying the result of part A on E, which is the subset of X, right? Because we know that the measure mu star of E is finite, we can use the definition of infimum and therefore we'll obtain that inequality. But now you cannot do that because the mu star of E might be infinity, and it doesn't make sense to write something smaller equal than something plus epsilon given one term is equal to infinity. So in that case, we separate them up. So because it is sigma finite, so the first thing we should do is we know we split our universal set into countable pieces, countable disjoint pieces, where each piece has measure finite. So mu naught of each measure is finite, and the union of those pieces is equal to the universal set X. So that's what we're gonna do. And we redefine, or we define EJ is equal to X intersect AJ, where the union AJ is equal to the universal set X. So we have EJs, right? And now what do we have? The mu. Now we have mu star or mu naught. Yeah, we have mu naught of EJ is less than infinity. So I need to correct something in my notes. So here we define this way, and we know this is, and here I should have written mu naught, I'm sorry, mu star of EJ is finite, because mu star of EJ is equal to the infimum of this collection, right? And notice that EJE intersects AJ with a subset of AJ, and therefore you can do a collection of this, AJ, this. So that this is an infimum. Mu naught of AJ. Okay, so well, it's just equal to this. And then this belongs to one of the elements in this collection. And actually it is the smallest one because well, wait, no, it's not. So this is smaller equal than mu naught of AJ, which is finite because each pieces is finite. So now you can apply A on each pieces, and recall that before we have given K, we can directly say there exists the BK satisfies certain properties using part A, but now we have to be a little bit more careful because fixed K, we have to deal J many of pieces simultaneously. So there exists a CJ such that this holds for every J. And then And then again, using the like the sigma algebra argument, you can get this is less or equal than this. And then now you can define Bj equal to the union of all of these pieces. You can gather them to get around. And then you have a series of inequalities, and then you have 1 over k. And then once you do that, you're basically almost done. You just need to define the ultimate b, right? So remember the graph that I draw. This is x and this is e. And so you're basically doing bk where k is equal to, for example, 1, and then this is bk where k is equal to 10. So what you're doing is you're doing intersection because you want to get the smallest one, right? So that's how you define your bk, which is the same, exactly same idea as in part b. And then you have a series inequalities. You got this. And then notice this does not depend on k, or this only depend on k. So you can take the limit as k goes to infinity, and therefore you obtain this. And then for the other reverse direction, we don't need the assumption that the mu star of E is finite. So we're done.